Thank you, Sean, for the introduction. My name is Tomohiko Taniguchi. Good morning to you all. I've been very much grateful for the opportunity I've been given by the INCOSE community to speak here today about the topic that you're now looking at. I am from a school in Japan where INCOSE handbook is every day read and studied by the students and the members of the faculty almost religiously. Some call it their Bible. So I'm very much pleased on my colleagues' behalf as well to be here. The only thing I have to request humbly is that send us your able students. We're ready to accept them, as many as possible. Now, my introduction, the career that I have had so far does not justify actually me speaking with you about a systems approach, systems design, systems engineering on such complex issues such as the bullet train. But I actually spent for 5 years with the company that is operating the so-called bullet train between Tokyo and Osaka. That's called JR Central. During the time I familiarized myself with the complexity of the entire system of the bullet train that's been running for, I don't know, nearly 60 years. 1964 was the year. So for me, I cannot speak anything about the Japanese bullet train without making a reference to this, which is about the great games that Tokyo hosted in 1964, 19 years after the Second World War. I was very small, like this. It was not actually my picture, but I would have been like that boy, bewildered by the introduction of this futuristic system and the bullet train. So if you speak with a generation of the Japanese above my age, you would certainly hear a lot of stories, a lot of narratives, a lot of memories even, that they have associated with the introduction of this bullet train, high-speed rail. It was duly called a dream express, which it was for small kids like me. Then, what is the system like? And let me spend a little bit of time to broadly speak about the essence of the system. These are existing Shinkansen systems. Shinkansen is a Japanese word. Shin represents new, kan means a backbone, and sen, a line. So it's a new backbone lines. And first, it started from Tokyo and went to Osaka. But over time, it's expanded to cover almost the entire part of Japan. But I'm going to focus my attention this morning not on all those, connections, but only this one, Tokyo and Osaka, because that was the first line laid out by Japan in 1964. So we're talking about the connection between two major cities of Tokyo and Osaka. The distance between the two is like this, 552.6 kilometers or 343.3 miles. And in order for you to put that into perspective, I put the similar distances. Kuala Lumpur to Singapore, 300 and 350 kilometers. London to Edinburgh It's almost the same. London and Edinburgh, 534 kilometers. Washington, D.C. to Boston, slightly longer. Sydney to Melbourne, 824 kilometers. And if you put a similar connection between London and Edinburgh, it would take just about this amount of time to be there from London to Edinburgh. Now, I must give you a quick caveat about the speed. The speed for train systems can vary depending on what kind of foundations you build the systems upon. In the case of Japanese so-called bullet train that connects Tokyo and Osaka, you've got many small corners, small curves. The radiation, the average radiation for those curves is as small as 2,500 meters. But in the case of French high-speed rail, the curve radius ranges from 4,000 to 6,000 meters. Obviously, the more bigger curves you have, the faster you could continue to run your high-speed rail. So we must be a little bit cautious whenever we speak about how fast your high-speed train can be. And after all, I'll show you an interesting example, which is this electric-powered car. It was built by Siemens of Germany, and it ran actually at this fast, 200 kilometers per hour. And guess when this was? Guess when this was? In 1903. So since 1903, we've been talking about high-speed rail that could run as fast as 200 kilometers. But commercializing this was quite a different story. Now, what of the illities? I first learned this jargon of illities by reading one of the seminal works of systems approach by Olivier Dweck, Engineering System, Meeting Human Needs in a Complex Technological World. And he said in that book, reliability, safety, flexibility, maintainability, the illities are central to any discussion of engineering systems. So I borrowed this idea and adapted that to describe the Japanese bullet train Shinkansen systems. First, safety. That's what differentiates the Japanese bullet train system from all other, I would say, high-speed systems, rail systems, because since its start in 1964, the Tokaido Shinkansen, that's the one that I'm talking about, that's connecting Tokyo and Osaka, has carried 10 billion passengers, but there has been 0 fatalities. No one actually was injured, let alone killed, by the trains. What about scalability? 15 services per hour. That's the high season number. Whenever leaves color in October, November in Kyoto, you have a huge number of visitors from all sorts of countries, and actually Australia is one of the biggest senders of tourists to Japan, so many of you might be familiar with the frequency of the services, but this many number is running per hour. So I put that in the category of scalability. What about reliability? Reliability, and I should say something like the following. average delay per service. We're talking about 400 and even more services running per day. And you've got snowy days, stormy days, rainy days, you've got earthquakes. And if you combine the total amount of delay time and divided by the number of services per year, you can get an average delay time per service. And for the year 2015, average delay time was an astonishing number of 12 seconds. 12 seconds. Please do something like this. Sizability. What about sizability? In terms of the number of passengers, each and every day it is running 450,000 people, and the combined sum per year is about 1,600 billion people. And that would make you even more puzzled why it is that despite the fact that the system is running this many number of people, they have had an ultimate perfect track record of zero fatality, so long as the passengers are involved. Maintainability. Well, I have to speak a lot about maintainability, but let's just make it symbolized by this car, which is actually very much popular among train spotters, because rarely you can see this yellow-colored car running on the track between Tokyo and Osaka. In my entire life, I have seen this car running only twice. And each time I regretted that I did not have a camera with me. But this car is running without getting detected by normal folks at night hours, like 2 a.m., 3 a.m., each and every day to check if there is anything wrong with the track, with the electric wires, and with the other systems. So maintainability has been kept pretty much in a good shape. So what of the key messages? And I think key messages must be described in very much simple terms. The system itself is, of course, very much complex, diversified, but the key message must always be a simple one. So I should say the following. Number one, foundational systems design. Foundational systems design, which I am going to be spending a little bit time on later on, has been proven pretty much robust. That's number one. Upgradability. Upgradability also proven scalable. Safety ensured by also the initial design. I said foundational design proven robust, and initial design also made it possible to maintain safety for the long period of time. But in order for this system to be built, to think the unthinkable, to think out of the box, the out-of-the-box mindset was needed. And I think that was embodied by a single designer, who I am going to introduce shortly. And also political economy mattered. In order for you to lay out this complex train connection system, you need to have a huge number of stakeholders in politics, in the financial community, in the local communities, and so on. The list goes on and on and on. So every time you build these train systems, political economy matters. So those are the things that I'm going to be touching upon. Now, what about the foundational systems? foundational systems created in the beginning, in the first place, when this train connection was launched in 1964. Conventional wisdom, if you think back at the year 1964 and ponder, try to remember how people depicted trains, I could point out these things. Firstly, the conventional wisdom held a new high-speed connection must use or must be connected to the existing rails to minimize cost and maximize network effect. There is a niche area in economics called transportation economics. If you open up any textbook of transportation economics, the author will tell you that network effect is something that you must value very much if you talk about the connections of trains. And also conventional wisdom held the high-speed rails must be locomotive drawn to reduce coach car noise. You can understand that. If you are in a coach car and the coach had a motor or motors, you must hear the noise of the motors. So the conventional wisdom at that time held the new car system, new train system must be locomotive drawn to reduce coach car noise and achieve crash resistance. You know what I mean? You've got a huge locomotive up front, and in the unlikely case of a crash between the two train sets, if you have a huge military tank-like heavy locomotive up front, the following coach cars may have a minimum amount of damages. So that was also part of the conventional wisdom. And if you look at the European examples, that's the one that the Europeans are still using. And then they also said it must run on embankment, given that Japan is earthquake prone. So those were some of the common sense views rampant held in Japan and elsewhere in 1964, in the 1960s. However, the system that I am introducing to you, the foundational system design, introduced dedicated elevated tracks only for the Shinkansen with no level crossings. And then separated tracks each for westbound and eastbound. Tokyo is east to Osaka. Osaka is west to Tokyo. And they created separated tracks each for westbound and eastbound. Those combined made it possible that there would be no need to prepare for head-on collision, especially with heavy freight train. If you mingle high-speed trains with freight carrier trains on the same track, you must be extra cautious, you must be extra prepared for a possible collision with very, very heavy freight carrier trains. But there was no such need right from the beginning. And I think that was the genius of this system's foundational design. And to make it very much graphic, let's take a look at the following slide. Well, it's this simple. Westbound track and eastbound track, dedicated separate tracks for each. Furthermore, special law was created to prohibit humans from entering the tracks. Elevated tracks made it possible. Well, there have been some attempts to climb up onto the tracks and enter the rail tracks, but they have installed CCTV cameras, one camera per 50 meters. So you get a huge number of cameras you're talking about, and one of those can easily detect the entrance of animals, human beings, other strange objects. And then the next moment, an alert bell was rung, would be rung, and then someone would rush to the point and wipe away anything that could cause hindrance to the system. So it takes a lot of elaborate management. And human factor also matters. I'll speak on that as well shortly afterward. So zero incident track record was thus made possible by these elements of the system. So it is now called system of crash avoidance. If you look at some of the elements that I have covered, you can now see that the system was so designed from the very beginning as would avoid any possible crash. And then safety, I can say, has been ensured by the initial design. That's what I mean. So this slide is to sum up, and let me just quickly take a look at this slide. Dedicated high-speed passenger rail service, that's what it is like. And the Shinkansen is operated on dedicated high-speed tracks. There are no freight or other passenger trains on high-speed tracks. There is no mingling. There is no chance of a crash with other trains. Full grade separation or no grade crossings, separating right-of-way maintenance from daily operations, and there is no possibility of a collision with maintenance of way equipment. Well, those pictures can show you that this is the bullet train, and there is no level crossing, so there is no chance of meeting with cars running on roads because there is no level crossing. And Shinkansen is running aside conventional rails. And these are slow running conventional lines. And then that's for the Shinkansen. So there is a clear separation between the slow moving trains and the high-speed rail. Here's another one that was introduced from the beginning. It's called Automatic Train Control System. ATC system prevents train-to-train collisions and overspeed derailments. There have been no train-to-train collisions and no overspeed derailments with ATC for 51 years. All operations and movements of a train set, including those in stations and maintenance facilities, are under full ATC control. High reliability of the ATC system is essential to realize highly frequent operations. A little bit of footnote here. The operating company JR Central is actually highly popular among the senior students of Japanese name brand universities. There's a perfect job safety with the company. I think it's one of the remaining examples of the Japanese way of management of lifetime employment, which was cherished, boasted, and looked at many years ago in the 1990s, claiming that it was part of the Japanese way of management, but the lifetime employment system is undergoing its fossilization, and very few companies are now employing this lifetime employment system. But JR Central is a clear example. If you are a high school graduate, and if you have a chance to meet other gender with the same company, also from a high school with no college diploma, by the time you get, both of you get 40, you can build a sizable house in a region where the land price is not as high as in major cities like Tokyo, Nagoya, Osaka, and then you can afford sending 2 or 3 even kids to private schools. So that's part of Japanese dream. And I think JR Central is one of those dying examples of ultimate stability you can get by getting employed. But anyhow, you may wonder, how come it is still necessary for the driver to sit on the control table like this? Well, that's a very good question. There was an incident or two 20 years ago that the driver was seriously ill, and he could not stay awake in the driver's cabin, but very few people detected it. And nonetheless, the train stopped at the designated station on time and left the station on time. So even if the driver loses conscience, even if the driver becomes seriously ill and cannot control anything, the train goes and stops as scheduled on time. But herein comes the importance of maintaining the human capital. Because if you are running 1 service per hour or 2 or 3 services per hour, it does not matter. But we're now talking about 15 services per hour. So you're looking at 1 service departing and another departing with an interval of 3 to 4 minutes. In order to maintain the accuracy and punctuality of the service, you must have a very much experienced driver to control, accelerate and decelerate in a very much elaborate way, so that the train will not delay and reach the station on time. So the clock or watch the train operator is using may be similar to the ones that you have, but when they speak of a minute, it is divided into 4 parts. So if I'd say this service departs Tokyo Station at 1:15 p.m., that 1:15 p.m. must be in the range of 1:14:45 seconds and 1:15:15 seconds. So it must be in the range of 15 to 30 seconds. So that's the kind of punctuality they say they have to maintain in order for them to run this much frequent this much frequency of the services. So total system approach, it may be a little bit different from the definition that you give from the INCOSE community, but this is something that they talk about, the total holistic approach of their system. Well, it's basically a confluence between the hardware and software, and the experienced drivers role that I just touched upon belongs to the yellow circle, employee education training, employee aptitude. I think that's something that still matters, even if you have a sort of hardware that makes almost automatic control of the system. Now, you can now see why it is that there needed no locomotive for the Japanese bullet train to run. And actually, there did not have to be a locomotive for this crash avoidance dedicated track system of the Japanese bullet train. But let's take a look at the differences between the locomotive drawn train set and the distributed contraction train set. Locomotive driven or distributed traction electric multiple unit system. So that's what the engineer of the initial design compared between the two. Between the two, the initial designer compared. The locomotive set above, when the locomotive fails, of course the whole system halts. The locomotive, in addition to that, cannot get lighter beyond a certain limit. And to accommodate the heavy locomotive, the infrastructure gets costly to build and maintain. I think those are all easy for you to understand. But over time, there emerged benefits of DTEMU, distributed traction electric multiple unit system. Inbound trains turn into outbound with no difficulty, that's one. Operational frequency rises as a result. And more importantly, motor technology has developed. So motor gets smaller, quieter, and lighter. And motor turns into brakes. That's so much obvious. Motor, electric motor turns into brakes, which itself generates electricity. So it's very much energy efficient and you may want to say environment friendly compared to locomotive drawn system. And the length of consist therefore earns variability as well. And upgradability proven, therefore, scalable. As technology advanced, if you look at the slide, the initial weight was that much per consist, and then it is now 700 tons. Acceleration, 1.2 kilometer per hour per second, now 2.6. And the train reaches 270 kilometers per hour in 3 minutes now. Height has also been reduced like that. And electric power consumed down by 32%. It's all due to the advancement of the traction technology, the advancement of the motor technology. So the distribution traction system and multiple motor unit system, they say, have been proven better. And here's an important point. I think railway, once built, will become a business of increasing cost. You must pour out your money into maintaining train sets, into maintaining infrastructure, into maintaining all sorts of things. So the cost should go up. But the Shinkansen, by making the core technology of motor advanced even further, decade by decade, it's made it possible to have a system of decreasing cost or increasing profit. And I think that's something that that's been rarely told. But I think that's what deserves more attention because the distribution traction system has made it possible. And railway's life cycle being very long, my suggestion is the model of decreasing cost, increasing gain should fit the best. But it was all out of the box thinking. Once again, it was not part of the conventional wisdom when the system was built in the early 1960s, because the then prevalent view still held. Train is history. Air travel, the future. Something called motorization. It's about the spread of family-owned, individually owned cars with the introduction of highway connections. Motorization was in vogue. And distributed traction, because there was no such example for high-speed rails in the 1960s, was viewed pretty much experimental. And it was a reason by which World Bank, when approached by the Japanese government, told the Japanese that it was very much experimental, so much so that the World Bank could not afford supporting your endeavor. And then to that assertion, there was one designer who said, "What's wrong with that? Why can you ever say this system is experimental?" And that's what the initial designer told the World Bank. And now is the part for me to introduce who he was. His name was Hideo Shima, the father of Shinkansen. He would later head Japan's space agency, JAXA, and he was the head of JAXA. And some of you might have been familiar with this name, associated with, not necessarily with the Shinkansen, but with the Japanese space agency of JAXA. So, introducing the designer, Hideo Shima, who he was. He was actually not a electricity train man. He was a steam locomotive designer. One of the steam locomotives that he designed before the war, during the war, was this. It's called D51, Model D51. And many of the Japanese train enthusiasts still love this type of steam locomotives. Some of them are still in good shape and running in a sightseeing in spots where scenic beauty is there for tourists. He was the father of Shinkansen, Hideo Shima, chief architect, and he was 1969 recipient, Asia's first, of an award called James Watt International Medal. The second awardee I learned was Henry Ford. And he, as I said, he was the first head of National Space Development Agency of Japan, JAXA. He would later become like this, and when he designed these systems, dedicated traction system, dedicated track system, and distributed traction system, separated tracks, no mingling with conventional lines. Many of his colleagues called him actually an idiot. But he was a pioneer who went, I should say, out of the box. And there was one crucial factor in his own life. During the interwar period, most fortunately, if I may say so, the Japanese currency was extremely competitive vis-a-vis the German mark. Of course, German mark nosedived. It lost all values you can imagine. So it was actually not expensive for a young engineer to spend long months and even years in Germany. During the interwar period, Hideo Shima was no exception. He went to Germany and saw something like this. It's called Fliegender Hamburger. Fliegender Hamburger. And he saw that running during his quote-unquote grand tour in Europe in 1936. And he said, probably he said, aha. That was his aha moment, because he saw a centipede-like consist should be used. And he meant, he had his instinct that the system of distributed traction should be introduced. That's because he spent so much amount of time and energy and effort in designing the heavy steam locomotive. And that was quite apart from the system that he was so familiar with. But he saw in the centipede-like, that's his own word, centipede-like system, a future. Here's political economic aspects. I've got 9 or 10 slides more. I'll stop shortly. Political economic aspects, what are they? There was one luck factor. Japan was under a narrow gauge regime. Narrow gauge regime. When the Japanese learned everything from the UK about the railway technology back in the 19th century, Japan was, of course, a poor nation. So some of those political leaders who were engaged in laying Japan's first train system thought that the narrow gauge, because it was narrow, would cost fewer in amount than standard or wide gauge. And then they would regret their own decisions later on. And then, understandably, the system of narrow gauge system had hit its upper limit as regards capacity. So there was a consensus among railway engineers and designers that to build a standard gauge system anew from scratch would be good. Now, I'm still talking about the political economic elements of the system involved. Budgeting, right-of-way, public support, time constraints. When you build a system like this, you must put into consideration all these elements, right? What about budgeting? It's got a special, unique difficulty. The Japanese government runs a yearly budgeting, the yearly budget. The fiscal year is the length, the ultimate length that they can think of. They cannot budget a budget for the length of 2, 3, multiple years. But building trains such as this obviously take a lot more than a single year. So the budgeting process is by nature hostile to this long-term project. political environment could change if you have a prime minister who is very much keen on building this system, but next year the prime minister might change. And that's unfortunately what's happened in Australia. Tony Abbott was very much enthusiastic of this idea, but Mr. Turnbull, when he came into office, chose to shelve the idea. And so the connection that they were talking about between Brisbane and Melbourne has so far been shelved. But in order to make sure that each and every year a certain amount of budget be given to this project, the builder, the engineer approached World Bank. The fact of the matter is, the support from the World Bank, financially speaking, was not so much of necessity for the project, but politically speaking, to be able to say that this project has been endorsed and being sustained and supported by World Bank gave them a very good cover or excuse with which they could urge the parliament and the budget designer to continue to give a certain amount to build the train. Right of way, it's always a problem because you're talking about not only thousands, but tens or even hundreds of thousands of landlords, each of whom claims her own property rights. So you must speak with all those people and let them give up some of their land properties for this train to be built. But fortunately for the system, there was a wartime legacy. There was a plan during the war for the Japanese government to build what was already then called the bullet train between Tokyo and the western part of Japan in order to make it easier for the wartime mobilization. So the wartime legacy proved positive in this particular case. What about public support? You need to thrill the public so that the public as taxpayers could subscribe to this idea of building the system. And then the idea of dream car, dream high-speed train enthused people like me, very little kid, and other people. And that coincided elaborately with Japan's coming out party, of maturing party, let's say, of hosting the Olympic and Paralympic Games in Tokyo in 1964. What about the time constraint? The same thing. Tokyo 1964 was actually the deadline, and many people actually had to concentrate their effort so that the system would be complete by that year. And then build cities and economies. What does it mean? This is one of the stations very close to Tokyo. It's called Shin Yokohama, the second stop from Tokyo. Yeah, if you go to Kyoto, the first stop is called Shinagawa, the second Shin Yokohama. Our school, Keio SDM, is actually very close to that station. That was in the middle of nothing when it was built. Shortly afterwards, it looked like this, but it's still very much not developed. This is how it looks like. Compare this and compare that. See this? And the stadium over here was the one used for the FIFA World Cup in 2000. I was there with my son, who was about 14, 15, and we were both very much excited that Japan won over Russia. Now, Japanese map looks like this, and we're talking only about this area. The green-colored area is the so-called prefectures that have the train connection. And now, what about the size of the economy? The Tokaido is the green area I'm now talking about. The area's GDP is about 1,987 billion US dollars. That's about 46% of Japan's total GDP. To put that number into perspective, may I say the following. Australia, New Zealand combined, 1403, Italy, 1826, Canada, 1553, South Korea, 1383, Russia, 1366. So the number 1987, you can say, is pretty much sizable, larger in amount than these examples. And it's very much, it's nearly impossible for anyone to see what the causal link has been between the building of the high-speed connection and the resultant economic size. It's really hard to see how these two are correlated. But as a common sense, you may want to say, without the high-speed connection, the green area would not have achieved this much economic size. Well, there must be many other things that I should touch. The last one, Uridas. Well, it's hard to pronounce, but it's actually a Japanese word, Uredas, beginning to shake. So it's a system to detect the first sign of quake, and then gives instantly the message and signal to the trains, all trains, to let them stop. So those are the systems that have been introduced, but suffice it to say, it's a complex system. You may want to say it's a system of systems, and the wholeness matters. Subsystems include many other things, which I have not been able to cover. Those are the subsystems. But let me just stop here to take questions from you. Thank you very much.